All right, we're going to go through chapter 8, which is going to be electron configurations and some periodic trends. All right, so when you're asked for an electron configuration, it's always going to be the ground state electron configuration. And what that means is the lowest energy configuration. All right, and so anything that is not the ground state would be a higher energy state, and all of those would be excited states. If you give a subshell that doesn't exist, say a 2D, which does not exist, all right, so this would be forbidden. All right, so if we started with hydrogen, all right, so hydrogen, the electron configuration of hydrogen is a 1s1. And so that is the ground state electron configuration of hydrogen. And so if I'm asking for the electron configuration of hydrogen, I want the ground state, which is 1s1. If I give a problem and I say my electron configuration of hydrogen is a 2s1, all right, so that would be an excited state, not the ground state. The 2s does exist, and so this would be an excited state. All right, if I gave hydrogen and said the electron configuration is a 2d1, that one is forbidden because a 2d does not exist. All right, and so we will go through the buildup principle, which is the Aufbau principle. And so you will need to know how to fill all your subshells. And so you fill the 1s first, all right? Then you fill the 2s, then you fill the 2p and then the 2s, and then you would fill the 3p and then the 4s, and then you would fill the 3d, the 4p, and the 5s, and then the 4d, the 5p, and the 6s, all right, then the 4f, the 5d, the 6p, and the 7s. And then finally the 5f, the 6d, the 7p, and the 8s. And so remember, the s's all hold 2 electrons. Those are all 2s. P's all hold 6 electrons. These are all 6s. The D's hold 10 electrons. They are all 10s. The F's hold 14 electrons. All right, and remember that you will also have the 5G, and that would be 18. All right, so there's one subshell in the first energy level. There's 2 in the second, 3 in the third, 4 in the fourth. There are 5 in the fifth. They didn't put in the 5G, but it should be there. There are 6 of them in the 6 energy levels. There is a 6F14. We don't know any elements there yet. There is a 6G18. Again, no elements there. And then there is a alphabetical order. You have your 6H, and note that they're always going up by 4, and so that would be a 22. And then 7 you would put across, 8 put across 8, 9 put across 9. All right. So after your 8s2, you would then fill your 5G18, then your 6F14, then your 7D10, then your 8P6, and then your 9S2. And that should do it for any extra credit problems, which would be give the electron configuration of futuristic element 150. And so you would have to then get to 150. This one will get you up to about 118. All right, so then you would have to keep going to get to 150. All right, so you should know this build-up chart, especially for the problems that are not on the periodic table. All right, so you don't have to memorize the buildup chart. What you do is you just look at your periodic table. All right, so this is the 1s1 and this is the 1s2. So this is hydrogen and this is helium. All right, so then you have lithium. Well, lithium is the 2s1. All right, beryllium is the 2s2. And then boron is the 2p1. All right, and so if you can remember that the first two columns are the S's, and they start at 1, and then 2, and then 3, and then 4, and then 5, and then 6, and then 7. They're the same as the period number. All right, and then your P's start at 2. All right, so there's the 2p, then the 3p, and the 4p, and the 5p, and the 6p, and the 7p. And the p's all hold 6 electrons. There are 6 elements over here for your p's. All right, and then your d's, you can count them, they're 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, and so the D, the 3D subshell, will hold 10 electrons. All right, now note the D starts at a 3D. So S starts at 1, there's the 1S. P starts at 2, there's the 2P. But D starts at 3. So there's the 3D. All right, and so when you go and look at the 3D, it gets confusing because it is in the 4th period, but it is the 3D. D starts at 3. All right, and when you go down to the F's, F starts at 4. So S starts at 1, P starts at 2, D starts at 3, F starts at 4. So that is the 4F. All right, but the 4F doesn't come in until period number 6. All right, so the period number only lines up for the S's and the P's. The D's, it's always one less than your period number. In the 4th period, you have the 3D. In the 5th period, you have the 4D. Best way to know is S starts at 1, and then you count down. 1, 2, 3, 4, 5, 6, 7 S. P starts at 2, and so you got the 2P, the 3P, the 4P, the 5P, the 6P, the 7P. D starts at 3, so you have the 3D, the 4D, the 5D, the 6D. F starts at 4, you have the 4F, and you have the 5F. And again, there's 14 of these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. All right, so if you're looking for element that is a 3s2, you're looking at this one right here. You go to the 3s, and this is your 3s2. All right, this would be, well, magnesium in your, so you'll be given a periodic table. You have to memorize where things are at, but that would be a magnesium. But you need to know that 3s2, you're looking at that block right there. If you want the 3d2, well, then you go to the 3D. 3d2 is right here. This is your 3d2. It is the 3D. It is the second one over. If you're looking for a 5f4, then this is the 4f. The next one down is the 5f, and we're going to the 4th one over, which is right here. Here is your 5f4. And so you should be able to find the block in this case, and then on the test you got the periodic table, and so it actually has the symbol of the element there, and so you can get the symbol of that element. Over here, if we had the 3p6, and then you go to 3p, you go to the 6th one here, and so here is your 3p6, because when you number them, that's 1 and 2 and 3 and 4 and 5 and 6. All right, so when you're looking at your S subshell has 1 orbital. So this is 1 orbital. All right, and so the number of the orbital is 0. And you get 2 electrons because the first electron goes up and the second electron goes down. And that's why there are 2 of the S's. You got an S1 and you have an S2. So you have the 3s1, you have the 3s2. Right? When you're looking at the P's over here, the P's have 6 electrons, which means that there are 3 orbitals. When you number your orbitals, the orbital in the middle is always 0. All right, and to the left, you have a -1. To the right, you have a +1. All right, and so there are your orbitals. And then you have to use Hund's rule, or the bus seat rule. When you put in your electrons, you will put one electron in each orbital, the bus seat rule. You're not going to sit with anybody until all the seats have one person in it. And then when you do go to sit down, you're going to sit as close to the front as you can. All right, and so once you have one electron in each orbital, then you will come back and you will pair up your electrons. All right, and in the Ds, you have 10, and so that requires 5 orbitals for the Ds. And so when you're looking at the D orbitals, there are 5 of them. Again, the orbital in the middle is 0. Then you have a 1 and a 2, and a -1 and a -2. And so again, you got Hund's rule, the bus seat rule. You're going to put 1 electron in each orbital before you come back and you pair up. All right, and so this is how you would put in the 10 electrons. First, you put 1 electron spin up, and then you would put the electrons in spin down. And then when you have an F, the F subshell, you have 7 because there are 14. All right, and so you have 7 orbitals. The one in the middle is 0, 1, 2, and 3 to the right, -1, -2, -3 to the left. And again, you've got Hund's rule, the bus seat rule. You're going to put 1 electron in each orbital before you come back and you pair up the electrons. So once you have 1 electron in each one, then you come and you pair it up. So there is a maximum of 2 electrons in each orbital. One has a spin up, the other has a spin down. All right. So you need to know where the S elements are at. You need to know where the P elements are at. You need to know where the D elements are at, and the F elements. You need to know where they're at on your periodic table. All right, so there are a few exceptions to the buildup rule, the prediction for the ground state electron configuration. Here are 2 of them. Chromium, when you do the electron configuration, it comes out as a 3d4 and then a 4s2. All right, so this is what you would get. All right, and when you look at the periodic table, you get your electron configuration, the buildup chart. This is what you would get. There is stability in half-full subshells. So when we look at our 3d4, we have our 5 orbitals, all right, and we have 4 electrons in them. All right, so that's a 3d4. When we look at our 4s2, that has 1 orbital and has 2 electrons in it. So what happens is this electron would rather go to the 3d and all be half full. And so with a 3d5, which is what our answer is going to be, 3d5 and a 4s1. And so that means that we have a half full D subshell and a half full S subshell. And so your chromium and your molybdenum have the same rule here. Now, tungsten does not follow that rule. That's the one below that. All right. And so your copper, your silver, and your gold all follow this rule. And so there are going to be 5 that you'll need to know. 5 exceptions to the buildup rule that you need to know. There are many others. There's only 5 exceptions to the buildup rule that you will be required to know. And they are for molybdenum and chromium, which has a half full D and S subshell, and a gold, silver, and copper, which are all in the same group, where it would be, if you did the buildup rule, it would be 3d9 and then a 4s2. And so what happens is one of the electrons from the 4s goes to the 3d and fills the 3d. And so there is stability in a full 3d subshell. And so your 3d subshell is full, and then your 4s subshell is half full. And so here it's completely full. All 10 electrons are going to be in your D, and then you're going to have a half full 4s1. All right, so the 5 exceptions you need to know, those are the elements: molybdenum, chromium, and then silver, gold, and copper. All right, rarely I will accept this. I don't know why anybody would do this. Would you write a complete electron configuration which shows every single one of your subshells and how many electrons are in each one? Normally, you're going to put a noble gas core, and then you will put the electrons that come outside the core. And so boron would have all of these, or if you put the noble gas core in, you would put in argon, the first prior noble gas. All right, so when we look here, this is the electron configuration of argon. All right, so you can write 1s2, 2s2, 2p6, 3s2, 3p6, or you can write argon. And what I would do to make sure that I had the right number of electrons is I put an 18 up here, because argon is number 18. All right, and so then when you add up, you have your 28, your 30, and your 35. So bromine's atomic number is 35, so neutral bromine would have 35 electrons. And you follow the buildup rule until you hit 35 electrons, and then you stop, and this is where you would stop. Now note, when you do the buildup rule, it comes out to be 4s2, 4p, no, it comes out to be 4s2, 3d10, and then 4p5. I don't care if you write it this way or if you write it this way. That makes no difference to me. The rule is you would write it in number order, which means that your 3 should come first. So you should move this to the front, which is what they did. They moved the 3d10 to the front. When you're following your buildup rule, the rule will say you put in the 4s2, then the 3d10, and then the 4p5. And so this is what it's going to look like when you are done. You are supposed to then put it in number order. If you don't do that on the test, I don't care. If you don't do it in the homework, I don't care. But if the computer is grading it, they might care. So if they're grading it harshly, they're going to make sure that you put it in number order. Again, I don't care what order it's in as long as they are all there. All right. All right, so your valence electrons, they are the S and P electrons outside the noble gas core. All right, and so your 3d10 is not called a valence electron. All right, your valence electrons, or your valence configuration, are going to be the S and the P electrons outside the noble gas core. And so we had argon, and then we had a 3d10, and then a 4s2, and a 4p5. So the 4s2 and the 4p5, those are your valence electrons. And so this one has 7 valence electrons, 2 from the S and 5 from the P. All right, when we are looking at your S and the P's, these are main group. So anything that ends in S and P, anything that's in the first 2 columns or the last 6 columns, those are the main group elements. Your transition elements, that's the D block. These are your transitions. Sometimes called transition metals because they're all metals, but transition elements. And then the F block, the blocks down here at the bottom, these are their inner transitions elements, sometimes called the rare earth elements. All right, so main group, again, so the main group is going to have S or P, Your transition elements, those are going to be the Ds. Your F block transition elements, I would call them inner transition elements. Seems ridiculous. Where are the F block? Well, they're in the F subshells. Okay, fine. Anyway, so you have your inner transitions, your F block, and you have your transitions, that's your D block. All right. So if we're doing arsenic, which has atomic number 33, so we find arsenic, it is number 33, so that means 33 protons. It is neutral, it's an atom, and so that's how many electrons it has. And so now we're going to do the electron configuration, and we will stop when we hit the number 33. So we have 1s2, then we have 2s2, then we have 2p6, and then we have 3s2, and then we have 3p6, and then we have 4s2. And note the gap that they put there, because they know what's coming next. They know after the 4s2 is going to be the 3d. And so they put it in number order, and now they're putting the 3d10 in order of numbers. So 1, 2, and then 3s, and now 4s. And then after the 3d10, you got the 4p3. And when you add all of these up, you get 33. All right. You can also put a noble gas core. So here you have, that would be a helium for that one. This would be a neon, and this would be an argon. So we have argon. And then we have 3d10, 4s2, and a 4p3. All right. So if it says, well, on the test, I'm not going to say give the complete. I'm just going to say give the electron configuration. If you give the complete, that's fine. If you give the noble gas core, which is what I'm expecting, that is fine, of course, as well. I never ask for the complete electron configuration. I just ask for the electron configuration. All right, so electron configuration and valence electrons of arsenic and zinc. So we just did arsenic. So remember, the valence electrons are the S and P electrons past the noble gas core. The noble gas core is argon. The S and P electrons are the 4s2 and the 4p3. So there are 5 valence electrons in arsenic. All right, so now we're going to do zinc. So zinc is number 30. All right, so zinc is 30. And so if we take 3 off, because arsenic was 33, we're just removing the 4p3. So it is the exact same, except we don't need the 4p3. And so the valence electrons would be the 4s2, just 2 valence electrons. All right. So zinc is transition metal. All right. You got 18, its valence configuration. All right, is not a 3d10, so it is a 4s2. The noble gas configuration is argon, and then 3d10, and then 4s2. And so your valence configuration is then the 4s2, 2 valence electrons. All right, so Hund's rule. We talked about Hund's rule. It is the bus seat rule. All right. The lowest energy arrangement of electrons in a subshell is attained by putting electrons into separate orbitals. So you're going to sit in your own seat until all the seats are full, and then you're going to pair up. All right, so that is called Hund's rule, also known as the bus seat rule. All right, so if we look at nitrogen, if we do the electron configuration of nitrogen, which is element number 7, you have 1s2, you have 2s2, you have 2p3. All right, so the S subshell has just one orbital, and we're putting in 2 electrons. The s orbital, the 2s, also one orbital. We're putting in 2 electrons. The p subshell all have 3 orbitals. Now, when we're numbering our orbitals, if it is just one orbital, the number is 0. If it is more than one orbital, the one in the middle is always 0. Negatives to the left, positives to the right. All right, and so when we put in our 3 electrons, we have to use Hund's rule. And so we have to put 1 electron in each one of the orbitals. All right, and so you will also be asked for the 4 quantum numbers. All right, so the 4 quantum numbers for your nitrogen. All right, and it's always for the last electron that you put in. And so we're looking for the 4 quantum numbers for the 2p3. All right, so the first quantum number is just the number. That is 2. That's always your energy level. That is the principal quantum number. That is the first quantum number. All right, the second quantum number is L, and it is either 0, 1, 2, 3, 4, 5, 6, up to n minus 1. Now, if you are L is equal to 0, that means you have an S subshell. If L is equal to 1, you have a P subshell. If L is equal to 2, you have a D subshell. If L is equal to 3, you have an F subshell. All right, and then it goes into alphabetical order. And so you have your G, your H, and your I, J, K, L. All right, so we don't know anything past F. We haven't made any elements in the G subshell yet. All right, so we have 2, and then we see P. So P's number is a 1, and so that is a 1, the second quantum number. The third quantum number is the number of the orbital that electron is in. So we put in 3 electrons. So we want to know where that third electron went. Well, the third electron went in orbital number 1. And then you either give a plus or a minus 1/2. Since it is spin up, that is a plus 1/2. And so the 4 quantum numbers for the ground state electron, the last electron that went into the nitrogen, is 2, 1, 1, and 1/2. All right, so remember when you're numbering, that's zeros if it's only 1. If it's more than 1, 0 in the middle, positives to the right, negatives to the left, all integers. Oh, and so you also see for nitrogen that you have 3 unpaired electrons. All right, and so that is going to be paramagnetic. If you are paramagnetic, then you are attracted to a magnetic field. If you have a compound or an element where all electrons are paired, so if all electrons are paired, then you are diamagnetic. All right, and so you are not attracted to a magnetic field. You will go right through the magnetic field. All right, so let's look at nickel. Nickel is 28. So you have your 1s2, your 2s2, your 2p6, your 3s2, your 3p6, and then you have your 4s2, and then you have your 3d8. And that is how you would put in the 8 electrons. All right, so you would have to go, and I would do it as your noble gas core. All right, so there's your helium, there's your neon, and here's your argon, and then 4s2, 3d8. Note that's how you would get it using the buildup, and that is fine. That's the way they put it here as well. The answer is always going to put it in number order, and the answer you will find is argon 3d8 4s2. All right, again, either answer, that's the same thing to me. All right, so what we want is we want to know what are the 4 quantum numbers for this last electron that went into our nickel atom. All right, and so again, we have to be able to number our orbitals. And so D has 5 orbitals because it has 10 elements in the 3D. And so again, the orbital in the middle is always 0. And then positives to the right, negatives to the left. All right, and so we're looking at the 8th electron put in, and this is the one that I'm circling. And so we see that we have a 3D. So 3 is the first quantum number. Remember your L, 0, 1, 2, 3, S, P, D, and F. All right, and so since we're in a D, we know that the second quantum number is a 2. All right, so now we see that the 8th electron ended up in orbital number 0. It is in orbital number 0. And now we also see that it is spin down, so negative 1/2. And so your 4 quantum numbers for the last electron you put into a nickel atom is 3, 2, 0, and negative 1/2. All right, so here we're going to ask if these are allowed or not allowed. And so the difference between excited state and a forbidden state. All right, so here we have a total of 2, 3, 4, 5, 6 electrons. The correct way to put in 6 electrons is 1s2, 2s2, 2p2. And that is the electron configuration of carbon. That is element number 6. That is carbon. All right, so that is not what happened here. But we do have 2 electrons in the 1s. We have 1 electron in the 2s. And we have 3 electrons in the 2p. And all of these things are fine. So this is just an excited state. All right, if you did something wrong, like put 3 electrons in one orbital, or put in a 1p that doesn't exist, then that would be forbidden. All right, and so that is allowed. It is not the ground state. It is one of the infinite number of excited states for carbon. All right, of course, now I can't see what that says. So that is 1s2, 2. I'm going to write that right on top of the next one. 1s2, 2s1, and that looks like a 2p8. All right, so this is a big problem because the 2p has your 3 orbitals, and they are numbered 0, negative 1 to the left, positive 1 to the right. You can't put 8 electrons in here. The maximum number of electrons that you can put into one orbital is 2. The maximum number of electrons that you can put in a p subshell is 6. If you try to put in 8, that is not allowed, which I call forbidden. Or call it not allowed. All right, if I have 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, all right, so we have to look at this, and it looks like everything is nice and normal. We didn't put in more electrons than need to be. But after we put in our 3p6 and we follow our buildup chart, next comes the 4s2, and then would come the 3d6. All right. And so what happened is they put the 4s2 electrons up into the 3d. And the d orbitals, there are 5 d orbitals. 0, negative 1, negative 2, 1, and 2. And so you can fit 10 electrons in the d. So having 8 electrons in a d subshell, that is perfectly fine. Having 8 electrons in a p is forbidden. It is not allowed. All right, and so in part C, it is not the ground state, because the ground state would put a 4s2 and then go to the 3d. And so C is the same as A. It is allowed. It is just an excited state. All right, and so this one, as soon as you see a 3d11, you cannot have a 3d11. D has a maximum of 10. That is not allowed. That is forbidden. All right. So in part E, they wrote out the orbitals because it's very important. They didn't just write 1s2, 2s2, because that would be fine. This has the 1s with 2 electrons in it. This has the 2s with 2 electrons in it. But both of them are spinning down, and that is forbidden. That is not allowed. In order to have 2 electrons in one orbital, one has to be spin up and the other has to be spin down. And so if they're showing both electrons spin down, that is not allowed. That is forbidden. All right, so we're going to talk about the magnetic properties, and that is all about diamagnetic and paramagnetic. So again, if you have one or more unpaired electron, you are paramagnetic. And if you are paramagnetic, you are weakly attracted to a magnetic field. All right. If you have all electrons paired up, then you are diamagnetic. All right, and it is not attracted by a magnetic field. And so this is when you have all electrons paired. And so diamagnetic and paramagnetic, you'll have to label those things and state how many unpaired electrons are in your elements. All right, so now we're going to look at some periodic trends. Let's do some more examples. No, fine. Periodic trends. All right, fine. All right, so when the periodic table was being organized, they could predict what the next element in that group, they would predict how it would act and how it would react with different things, because your groups, your elements in your groups, react very similarly. All right, and so Eka means the element below aluminum. All right, and so he could predict all of the different properties that the element that is under aluminum, so it's in the same group, and then the element under boron, again, the same group, just under boron, under silicon. And so he could predict the characteristics of the elements that were not yet known, but he could predict how they would react due to periodic trends. All right, and so the elements are not just put on the periodic table in some random order. They are arranged by their physical and chemical properties. So again, the columns of elements will react very similarly. All right, so we're going to look at 3 periodic properties, and that is the radius. All right, so for the radius, the atomic radius, fluorine is the smallest. All right, and so it's going to decrease as you go to fluorine, and so it's going to decrease as you go to fluorine. That is your atomic radius, and we will see a chart for that. Ionization energies and electron affinities. All right, so ionization energy is going to form a cation. All right, so you're going to lose an electron and become a cation. That's an ionization energy. You can lose 1 electron and be +1, a second electron be +2, a third electron +3. Then we're going to look at electron affinity, and that is when you're going to be an anion. And so that is when you're going to gain an electron and have a negative charge. All right, so your atomic radius, all right, and so the trend, vertical column, the atomic radius increases with your period number, so you're getting bigger as you go down. Again, fluorine's the smallest, and so it's decreasing as you go up. That means it's increasing as you go down. All right, and so then, of course, then a horizontal row, as you go to the right, you are going to get smaller. All right, so here is your atomic radius chart. All right, and so you've got your different atomic radii. So I normally don't put in the noble gases, but the noble gases are in there as well. So again, as you go across a periodic table, lithium to neon, you keep getting smaller. As you go down the periodic table, lithium to sodium to potassium, you are getting larger. And so your periodic trends, again, I always ignore the noble gases, but you can put in the noble gases as well. All right, so you're going to decrease going this way, and you're going to increase going this way. And so When you go from lithium down to neon, you see that you're getting smaller. That is the decrease shown here. When you go from lithium to sodium to potassium, which are in the same group, as you go down the periodic table, down here, you are increasing the size of your radius. Here's the picture of the atomic radii that are shown. All right, and so again, the smallest is going to be, well, helium. So I should not pick, just no reactions are really occurring with helium. We use them to cool NMRs and MRIs and fill balloons. And so anyway, we have the smallest is going to be your helium. So again, you're going to decrease as you go to the right. So as you go to the right, you will see them getting smaller. You're going to increase as you go down. As you go down, you're going to increase. So you're going to see them getting larger as you go down. All right, so this periodic table is very nice to use for our electron configuration. So let's do a few more electron configurations. All right, so if I look at magnesium right here, so what I can tell about magnesium electron configurations is this is the 1s, this is the 2s, and this is the 3s. And so I know that magnesium is a 3s2. All right, so I know that that's where it's at. It's in the 3s2. Now, if I want the electron configuration, I have to go to the first prior noble gas, which is neon. And so I would put neon in brackets, and I always put the 10 here. That's not required, but I want to know that I have the right number of electrons. All right, so I have 10 for the neon, 2 for the 3s2, and that is my total of 12 for magnesium. All right, and so if I want my 4 quantum numbers for magnesium, the first quantum number is the number 3. So it ends in 3s2. So 3 is my first quantum number. Then you have to remember your L's. So the L quantum number, it's 0, 1, 2, 3. It is SPDF. And so since we are a 3s, the second quantum number is a 0. All right, for the s's, there is only one orbital. And so that orbital number is 0. And then you put in 2 electrons. First one goes spin up, the second one goes spin down. And so that is a negative 1/2. And so the 4 quantum numbers for magnesium is a 3, 0, 0, and a negative 1/2. If we pick iron, iron is right here. All right, so if we are picking iron, we see that S starts at 1, the P starts at 2, so this is the 2P, here's the 3P, here's the 4P, here's the 5P, here's the 6P, and then the D start at 3. So this is the 3D, and this is the 4D, and this is the 5D. All right, so this is the 3D, and then we got to count how many over. This is 3D, 1, 2, 3, 4, 5, 6. And so we're looking at a 3D6. If we want the full electron configuration of iron, it has the noble gas core argon, which takes up 18. All right, after argon comes 19, which is potassium, which starts the 4s. And so then you have a 4s2, and then you have your 3d6. Also, we didn't answer that for magnesium. Note that everything is paired up for magnesium, so this is diamagnetic. All right, so if we do our 4 quantum numbers for iron, all right, so we're looking at the 3d6. You have to know that you have 10 elements in the D subshell, which means you have to have 10 electrons, which means you have to have 5 orbitals. You also have to know when you number your orbitals, the one in the middle is always 0. Then you got a 1, 2, you got a -1 and a -2. All right, and so we're going to put in 6 electrons. Again, Hund's rule, the bus heat rule. You got to put 1 electron in each one of these orbitals, and that is 5. And then you need 1 more because we're doing 3d6. And so we see that that is in orbital number -2. All right, and it is spin down. So our 4 quantum numbers for the 3d6 is a 3. The D, we come up here for the L, D is 2. All right, and then we are in a -2 orbital number with a spin that is going down. And so the 4 quantum numbers for your iron are 3, 2, -2, -1/2. And this has 4 unpaired electrons, and so this is paramagnetic. All right, if we pick one over here, which one do we want to pick? Oh, let's do sulfur. All right, so sulfur is right here. Sulfur is number 16. All right, so we see that sulfur is in the P's. All right, P starts at 2. It is in the 3P. It's the next one down. And it is 1, 2, 3, 4 over. And so this is a 3P4. So we know that the electron configuration for sulfur is going to end in a 3P4. If we want the full electron configuration, the noble gas, first prior noble gas is neon. That is 10 electrons. After 10, then 11 is sodium. Sodium starts the 3s2. And then we go to our 3p4. And so you have 10 from your neon, 2 from the 3s2, 4 from your 3p4, which is a total of 16. All right, and if we want our 4 quantum numbers for the 3p4, all right, so our 4 quantum numbers for 3p4, the first number is the 3. Now p, up here with the L, p is 1. All right, so that's a 1. And then we know that there are 3 orbitals for the p. All right, and again, when you're numbering your orbitals, the one in the middle is always 0. 1 to the right and -1 to the left. And we're putting in 4 electrons. Hund's rule, Busseit rule, 1 is going up in each one of the orbitals. Then the 4th one is going down in orbital number -1. So it is in orbital number -1 with a spin down. And this has 2 unpaired electrons, and so this is paramagnetic. All right. They don't have the F's up here to do an F problem, but all right, electron configurations are going to be very important, and the 4 quantum numbers. All right, so when you're looking at bromine, Se and Te, Br, Se and Te, Br, Se and Te. All right, and you want to put them in size order. When you go down, you are larger. Te is the largest. When you go to the right, you're the smallest. So Te is the largest, and Br is the smallest. And so when it says to put them in increasing atomic radius, so you want to put the smallest first, that's bromine, then Se, and then the largest last, and that is your Te. All right, we will go through ionization energies next time.